Okay, we are live on YouTube. Okay, good morning and welcome to yet another online Chai and Y session. So, for those of you who are watching on YouTube, the first thing is, in case you can't hear me, please put a shout. Put a comment in the chat box. Similarly, on Facebook, if you can't hear me, please put a comment in the chat box. I hope we are live on YouTube and Facebook as well. And it's a pleasure to welcome you to the Chai and Y session. So let's just do a very quick check of the sound. Can you see me and can you hear me? Because there is no screen sharing today. I'm just going to do a few experiments. So if you can't hear and see me, that's not going to be fun. So let's confirm that you can hear and see me on Facebook and YouTube. Any responses? Who's checking YouTube? Just check the comments. Just make sure that people can hear us. I must thank Divya Shankar, who is actually remotely watching this and is doing the Facebook feed. And people, we have Sneha, who's checking our YouTube feed, and I hope it's okay. All right. So we are still in the ending of the unlock phase, but still not able to be out at Prithvi Theatre as we should be on the first Sunday of the month. So here we are, stuck in TIFR, and we thought we got a lot of requests that, yes, the lectures are good, but especially with kids, we really want to see these experiments, the simple experiments. So can you show us some more experiments? And we've pretty much done all the experiments we had in the Justice series. But then we found there were a whole bunch of experiments which we didn't do with when we were doing just a bit of water, just a bit of sheet of paper, etc. We found some more experiments. And the common theme for all the experiments today is actually air pressure. Air is all around us. Air exerts pressure. This part we've all heard. But sometimes you can do some very, very simple things and see this in a nice way. So yes, instructions. If you are watching on YouTube, please put your questions as chats in the box, and we will try comments in the box, and we will address them. And if you're watching on Facebook, also please enter comments, and we will try and address them. If they are urgent, we will do it right in the beginning, in the middle of the thing. Otherwise, we will take them one by one at the end. But don't worry, we will try and get you your questions as far as possible. So yesterday was Teachers' Day. I hope you thanked all the teachers, and teachers are not just the teachers in schools and colleges. We learn from everyone around us. We learn from the world. We learn from doing things, and we will learn from simple things that we do. If you're in Mumbai, you must have noticed that the last couple of days, the sun is out. It's gotten really hot. The monsoon seems to have taken a break for now. And, I came here this morning, and amazing thing, nobody has touched my experiments since I last did them. They're just lying, or everything I used is lying here. And I found this really dirty bottle of water that I used. And I said, I wanted a glass of water. I'm going to pour the water out. And what I'm going to do is, can't make a mess in TIFR. I'm going to try and pour a bottle of water out. So by the way, if you're joining us at home, just make sure you have a couple of water bottles with you, and some string if you want, but even just a couple of water bottles is good. Any size, it doesn't matter, a liter bottle should be fine. So how long does it take? Okay, so we're going to do an experiment. Where is Suren? Where is Suren?
I'm here.
Suren is here. Okay, Suren is here. Suren, you have a stopwatch or something? You can help me time this?
Yes, sir.
Everybody has a mobile, which is everything these days.
Yes.
So if I want to pour the bottle of water out, 1 liter bottle full of water looks very dirty. How long does it take to pour a bottle of water out? Let's do this experiment, and there's something which you can very easily do at home. And all I'm going to do is turn the bottle upside down. Done. About
11 seconds.
It took about 11 seconds to pour the bottle of water out. Now, can I do it any faster? And of course, we should not believe it when it's done once. Ideally, you would want to repeat this thing, do it a couple of times.
But now you already poured all the water.
I poured the water out and I can't pour it back in.
But we have another lovely experiment.
So the thing is, how long does it take to pour a bottle of water out? And what can you do to pour it slightly faster? So actually, we have another experiment, and this is one of our most favorite experiments. And this is something which I will explain slowly. But in this, we will have to pour it out and pour it back. But what we have is, we have 2 bottles of water. Can you just check that the tilt is such that the table is visible?
Yeah, it's perfect.
Okay, you can see these 2 bottles of water. There's an empty bottle of water, and this bottle of water is full. Okay, and the idea is again.
How can I do?
Wait.
Add something?
I will do one thing. I will just make it easy to see. I'm going to add a pinch of a little dye. At home, it's much easier for you to see because you can see it. But
yeah.
I'll just add a little bit of color to it.
And you can see something going down.
You can see the color mixing. Isn't that beautiful? Just watch this. Just watch this. In fact, I can hold it nearer the camera, perhaps. Isn't it beautiful just to watch color? I'll hold in the white background here.
Yeah, it's perfect.
Okay, isn't it? Sometimes it's just beautiful to just watch things slowly. And we will put a little bit more. Okay, good. And I'm just now going to do it a little quicker. I'm bored of waiting for that color to mix by itself.
No, don't do that. It will mix automatically when it turns down.
Yeah, anyway, so here it's probably slightly better for you to see that there is water in this. It's this bluish thing over here is just water. And what I'm going to do is I'm going to pour water out, and I want to do this many times. And it's really a pain. It's a pain to having to keep, if I use my basin over here, if I bring this thing, I pour it out, it's a pain to have to pour it back. So what we designed was a simple way to pour water from bottles without making a big mess and making it easy. So these bottles originally would have had their caps, yeah, the bottle caps. So this will take some time, but at home you can go to the tap and fill it and do it. But out here I can't keep filling bottles and bottles of water. So what we did is we made something which connects these things together, and that is this little thing. And maybe Suren, you can hold it near the camera so it can be seen what it is. Just look at the screen so that you know what the view is. So basically what we've done is we've taken 2 of these caps and stuck them back to back. Okay, and then stuck them with some glue, and then made a hole through it. Just take a hot rod or something and just make a hole through it. So we have something which has a 2 caps stuck together with a hole through it, and even better, just to make sure water doesn't leak out of something, we've even put some tape. There's some tape around the hole.
And
okay, and it's been fixed with araldite. This is a good permanent thing. But even if you make it at home, it's okay. You can spill a little bit of water here. I don't want to take a risk of spilling any water. Hence this. So what we do is we put this little cap on the bottle, and this actually allows me to do one thing, which is connect these bottles one on top of the other like this. And yeah, I probably don't have this at home, but you can watch what happens. So now you have a bottle which is connected. Of course, this is slightly bigger. This is 1.5 liters. Earlier, I did this with a liter of water. And of course, the hole is slightly smaller. because the hole was earlier, you had the mouth of the bottle was open. Now you have a hole in this. The hole is about 1 centimeter in diameter. That's the hole like it. Your finger goes through it, little finger. Okay, and now I am going to tilt this upside down. Okay, so we'll tilt this upside down. Actually, can you just turn the screen so I can see the screen as well? I have no idea what I'm doing. Fantastic. And can you just put it on speaker mode so I see myself? That's okay. Don't worry. It's fine. I'll do it when I'm there. Okay. So let's see. We're gonna do this. We're gonna do this again. I'm gonna turn this upside down, and we're gonna time how long it takes for the water to fall. The water is falling. The water is falling. Can you see the bubbles? You can probably hear the bubbles going blop, 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 blop. It's going to take some time, so I am going to just go and set this right. But you can see it's following very slowly.
After 50 seconds.
Okay, so it's almost been a minute. It's almost a minute, and the water is still going glob, 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 and it's falling very slowly. So why is the water falling so slowly? So again, you can decide what's happening. And can you see the bubbles going up? Bubbles are going up one by one, and the water is falling almost, I would not say drop by drop, but in little spurts, it's falling slowly. It's trying to speed up a bit now. Stop. I thought it was speeding up, but hey, look at this. This has stopped. This has stopped. Wait. This is a good time. Since it has stopped, I'm going to actually move it so that it's in front of the white screen. It's the wrong way. That way. And it starts again. A little bit of jerk and it starts again. But this is good. It's taking some time. Sneha, how long has it been since it started?
1 minute 40.
1 minute 40 seconds.
48.
14.
Almost
48.
2 minutes.
Okay, almost 2 minutes. Coming up to 2 minutes, and we are not even half done with the water. So what's going on? Maybe do you want to put in something in your chat saying that why is it? Think Divya, if there are answers coming on Facebook, please let me know what people are saying. And if there's something on YouTube, you can just leave the timer here. It's okay. You don't have to hold it. Thank you. So 2 minutes 18 seconds. Okay, we have to do this once at least. I know this is a rather boring experiment to wait because it's going to take about 3 minutes for the water to drain.
4.5.
So yeah, anyone on YouTube saying why is it so slow? Why does the water not pour out? I mean, the bottle was empty below. This bottle was full of water. You saw when I just upturned it. Well, I agree that the hole is not so bad, but we can do an experiment. We'll do the correct experiment. Suresh, why don't we do one thing? Just go fill this with water. We'll put the cap on it and go through the cap. That will be the right. Okay, so yeah, come on, guys, come on, pour. Come on, don't stop. Okay, we're almost there. It's gonna get done. Any comments? Nothing on YouTube.
Oh, crowd at the mall.
That's a brilliant. That's actually whoever said that. Fantastic. Somebody said this is like a mall where there is a crowd and there's only one exit or entrance. And that is perfectly a good analogy. That is absolutely correct. This is very similar to a traffic congestion problem. Earlier, we had water on top and air at the bottom. And remember, because of this little connection that we've made between the bottles, it's sealed. So the water cannot come down unless the air can go up. Yeah. So water can't go down unless the air goes up. And there is this little one point, and this happens at a railway station, at a mall. People are trying to go in, people are trying to go out, and there's only one point, and there's going to be a traffic jam over there. And that's exactly what is happening. Air and water are fighting over here. Air wants to go up, water wants to come down, but there's only this little thing. And hence it takes a time, and it's 4 minutes and 9 seconds. I have this stopwatch going here. 4 minutes and 9 seconds should almost be done. We will give it a bit more time. till we can do that. So that was a very nice answer. That yes, this is like crowd at a mall because we have a thin constriction here through which air wants to go up, water wants to come down. So they are fighting over there. Not a happy situation. Now we can see what we could do to make it slightly easier. But before that, we should compare the 4 minutes and whatever it takes with. Okay, so earlier we said 11 seconds for a bottle of water, but that was through the full opening. So what we will do is we'll take the same bottle of water and we'll connect one of our, we'll connect this exactly the same tube, this double jointed tube to the mouth of it. So this is.
No,
this thing is. Can you break this? Just break this off. See this. If you're doing it at home, one more thing to notice: if you want a good seal, please remove this seal. You see this little plastic strip at the bottle. This prevents you from tightening it. So if you're doing this, it'll be easier if that's gone. So we just remove it so that it can be tightening. 5.5 minutes. This is amazing. Sometimes when you do this experiment, it decides not to behave, and there's something happens and it goes out very quickly. But today it is taking its time, and it is taking 5.5 minutes plus. Are we done? That is a tough bottle. Maybe now it will come out as stretched. Cut it. Okay. Good. So that is out. It will be easier for me to screw this on. No, I think it's slightly different.
Six number.
Okay, whatever it is. So this is it. Some water is going to leak from here. Agreed. And we're going to time this. Oh, this is. Let's finish this. Let's finish this experiment.
No, that's not going.
It's still not gone. Yeah.
It will not go.
Oh, this is now stuck. Okay, so this is with some, thoda sa bhaiya. Hato karke, come on.
आटे वाले चक्की का भाई.
Yeah, this is like thoda sa, yeah. Let's not squeeze the water. That's a different way of doing it. Okay, so we will say 6 minutes and 46 seconds, 6 minutes, 47 seconds. So that took 6 minutes, 47 seconds. And now I'm going to do this. Remember, this is 1 liter. This is 1.5. We'll scale that, but with the same smaller hole, if it takes anything, last time was 11 seconds for the bottle. So let's put it this way. Time. So it is a little slower, certainly. And you see the problem is even without the bottle, this is much slower.
Now pull it.
Okay, what can I do? I can either squish the bottle. You must have seen some people when they pour cold drinks and they just try and squish it. I can try and tilt the bottle. I could tilt the bottle. That's one solution. See, if I tilt the bottle, it's actually flowing out in a more smoother way. But there's one more thing I could do. I could turn the bottle a bit, swirl the bottle. And now see what happens. Did you see it suddenly sped up? It speeded up. And this is the beauty of this experiment. You can do a very, very beautiful demonstration of what a tornado looks like in the world. And this tube is, this is often called the tornado bottle experiment. So what I'm going to do this time is I'm going to invert the bottle. Okay, you can start the timer again if you want. And this time I'm going to try and shake it, twist it, and there we go. Can you see a little tornado forming in the bottle? I should. And we'll bring the camera in close so we can see this again. We will do this one more time. But right now we're just timing it so we can see how long the water takes to come out. Now earlier it was 6 minutes and 47 seconds. And this time, after making sure that we got this little tornado started off, we are done.
34 seconds.
34 seconds. Okay, so let me do this again. And this time I'm going to hold it near the...
Bring it closer.
Bring it closer here. Get this thing started off. You've got to give it a little swirl, and there you go. Now, can you see the tornado in the bottle? See the tornado. Okay, it's got stuck again. So about 40 something seconds.
45 seconds.
Do this one more time. Anyone wants to see this one more time again?
I think we'll do it for one for the road now.
Okay,
Now
one.
there are some more exciting.
So we'll do these things. We will do these things. Okay, now, was that fun? Right? Okay, it's nice and cool. And this, what you saw, the shape you saw, is exactly the same shape. If you look at a picture of a tornado that happens, we don't get too many tornadoes in at least in around here. But when you have tornadoes outside, which are these whirling storms, it's a very, very similar thing. Now, why did it fill so quickly? I need my bottle to explain here.
Oh, sorry.
We're not done. Why did it happen so quickly? Remember what was the problem? The problem is this is fight between air and water. Okay. And when I tilt it, obviously now when I start this, let me start this tornado again. What happens is at the center, come on. Yeah, this column is basically empty, it's air all the way through. So air has a very direct path to go out. The water is coming from the sides. In the center, there's no water, there's only air. So it's basically like a hollow little pipe through which the air can go up and the water can peacefully come from the sides down there. And that's why this cleared out so quickly. Okay, so you stopped this. Earlier you had a bottleneck over here where air and water were sort of fighting to come out. Now the air has a very easy path to go through the center, which is a hollow in the thing. So that's the reason why this thing happens so easily. Any questions on this? Any comments?
Not on.
Divya Shankar, who's monitoring Facebook. Anything on Facebook?
Nothing on Facebook.
Okay, so yeah, I hope you like this. So you can build this at home. Remember, if you're building it at home, let me just tell you again what you should do. You should take two little bottle caps like this. If they are, you can take them from identical bottles. Stick them together with some glue, Fevikwik, whatever you have, Araldite, and then make a hole. And the easiest way to make a hole is actually to take a hot object, put it in the fire and just push it through it. And then if you take a hot object, you don't even need glue. If you melt the plastic, they'll stick together anyway. But it's always better so you can just stick it like this. This is just stuck together. But it's always better to take some tape and put some tape around it so that it's a little bit more sturdy. And you can see we've actually melted these and made holes. So that's how they look. But that's a little tube. But this little tube allows you to connect these two bottles together, and you can then play with it and have a lot of fun. Okay. All right. So I have spilled some water, which is usual of me, but hopefully they won't mind too much. All right. Let's do something more with bottles. Yeah. Let's let's do just the blowing in the bottle. Yeah. Okay, so this was our tornado tube, and now we're going to do another fun experiment with a bottle, with an empty bottle. So there's just an empty bottle, and let's see, empty bottle. You can see the empty bottle. Wait, you look here. Yeah. Okay. So there's an empty bottle, nothing in the well, you did have something in the bottle.
Yeah,
but let's crumple some. We have some tissue
paper. Yeah.
Here's a roll of tissue paper. So I'm going to take some tissue paper. You can take newspaper, any paper, just some thin paper. Okay. And we'll just crumple tear some paper. We'll crumple it. Okay. And put it in the mouth of the bottle like this. Whoops, that went inside. I think I need a little bigger piece. A little bigger piece of paper. So you want something like this. Okay. You want something like this, where there is a piece of paper which is stuck at the mouth of the bottle. Okay. So I'll give you a bit of time to get yourself a bottle if you want, and just make something which is, just crumple a little bit of paper and put it just at the mouth of the bottle. Okay. Just at the mouth of the bottle, there's a little bit of crumpled paper. There it is. Okay. Now, this is a trick experiment. You can have some fun. You can try. What I want you to do is, I want to see how strong you can blow. right? All I want you to do is keep it here, okay? Keep it at the mouth of the bottle and use your breath to blow it inside the bottle. Okay, so I'm going to have to keep it down here. And just put it the, okay, raise it a bit. Okay, so there you are, you see the bottle. And if you don't have a piece of paper, you can just take a small piece of thermocol, maybe. Oops, there it is. So whatever, you just take a small piece of thermocol or paper. I'm going to keep it here. And now the aim is to use your breath. Don't touch the bottle. You can't touch the bottle. All you need to do is blow it inside the bottle. Okay, and 1, 2, and 3. Once again, let's try the paper. Thermocol, maybe you did something with thermocol. I don't know. Experiment said do it with paper. You're going to do it with crumpled paper. Okay, 1, 2, 3. No, it didn't go in. Came out. You tried?
Yeah.
You're better than me.
Same piece of paper.
Same piece of paper, same piece of. You can try.
No, it's okay.
We'll try with both. We'll try with the thermocol.
Okay.
There it is. It's
yeah.
in the bottle. Wait. Oh, cheating! He's using a straw. He's using a straw to. You pushed it with the straw.
No, I did not.
He pushed it with the straw. He pushed it with the straw.
I did not.
I saw.
Okay. No.
This first thing you got to blow away. You know, this is
okay.
Fine.
Okay.
I think you pushed it with the straw.
No, I'm not cheating.
You should never trust Suren uncle. Suren uncle always tries these tricks where he does something. Wait, 1 second. There you're pushing it with the straw.
No,
why don't you just get the straw out of the way for now? Oops.
Okay.
Wait, get the straw out of the way. Just blow with your breath. I want you with your breath put it in.
I'm not a Superman. It's going to blow off.
Okay.
The bottle blew beyond.
The bottle blew,
paper flew off.
The paper flew off. The thermocol flew off.
So there was enough pressure developed.
Okay. So now clearly you're blowing strong enough.
Yes.
Time maybe. Actually, you want to try this? Neha, who's here, we can ask her to try this. You keep a ball of paper. Yeah, we can see, like, you can think we are cheating or doing something. We just get Sneha, who's here. All you need to do is just blow it and see if you can get the ball in.
What cheating did you do?
I didn't do anything.
Okay. She didn't blow hard enough. That was the reason. Okay. But in general, when you do it, when you do this experiment, you will find that when you blow, most likely the thing comes out. Okay. And the answer is very simple. There is already air in the bottle. The bottle is full of air. If you push more air in it, the air in the bottle does not like to get compressed. It doesn't like to get more air. It's already happy with whatever air is there. The pressure inside will increase. And as the pressure increases, it's going to push whatever is the extra air out. And there's a very light piece of paper, it's going to fly out. So that's why in most cases, I don't know how she pushed it in. I really don't know how she pushed it in, but it goes out.
Okay.
And
let's prove the trick now.
The trick, if you want to actually push it in, get the thing in, is simple. Reduce the pressure inside somehow. If I reduce the pressure inside, it automatically wants to push stuff in. And that's what actually initially Suren had tried to do with the straw. He was not blowing air. He was actually,
the ball becomes too.
We've crumpled it too much and made it a nice
ball.
Yeah, crumple some more paper. No?
Yeah, it's okay.
So he's actually going to, that's fine. What he did was he sucked the air into his mouth. When he sucked the air in, it reduced the pressure in the bottle and the paper went inside. And we can try it with another thing.
Okay, you want to use the lighter one?
That's fine. We can try it. Okay, do this again.
Same paper.
Can we bring this somehow closer?
Closer?
I can bring this closer. No, it's okay. You do it. I'll adjust it.
Is it focusing correctly?
Yeah.
Okay. You have to slide the straw free without touching the ball or the wall of the thing. Take it as far in as possible and suck the air.
And there it jumps inside.
Okay, fine.
Not too bad.
So far, so good.
So what did we learn? We basically figured that there is air in the bottle already. There was a lot of air in the bottle. The air does not like to get compressed. The air does not like to get compressed, and hence if you blow hard, it actually pushes it out. On the other hand, if you suck the air, okay, I need to adjust this again. This is not going down. It's cutting my head off. So it just goes back to the original position.
Yeah.
Okay. So yes, you had air in the bottle. Air doesn't like getting compressed. If you blow, it throws it out. Whereas if you suck it, it pushes it in. So next time somebody asks you to do it, you can do this as a trick. You know what to do. Okay. Good. And this idea of air, resisting any change in its thing is just so easy, and so it happens everywhere. For example, if I have a sheet of paper, I have 2 sheets of paper with me, right? Now, clearly, if I drop this paper, it took its while in falling down, right? Drop the sheet of paper. It sort of floats around a bit. On the other hand, if I crumple the paper, same weight hasn't changed. It just falls straight, right?
Why don't you do both the same time?
Both at the same time. Crumpled paper, same sheet, same size. One of them will float around for a while. One of them will go flat because the air anyway doesn't like things pushing it. There are things, we can't say it, there are molecules everywhere, oxygen, nitrogen, whatever there is in air. These molecules don't like being pushed around. This is small, it doesn't offer much resistance. It goes through, this is slightly larger. So it offers, the air molecules are impeding it somehow. They're stopping it from falling down. And of course, the shape is very important. There are other things which we have talked about in some earlier sessions. But how do you know this? How do you know? I mean, how heavy is air? Have you ever thought of it? So let me ask you a question. Actually, I'm going to ask you 2 questions because one of them I really want you to put your answer down. How heavy? So what do you think is heavier? Is the air in the room that you are at home, wherever you're watching, is the air in a typical room heavier than you? Who's heavier? The air in the room or you? Who's heavier? Okay. So that's a question for you. Of course, clearly you'll say, oh yeah, these guys are in a big hall over here, so it must be heavier. But no, even in a small room, let's look at a typical, Mumbai-sized apartment, one room. How heavy do you think the air in the room is? And can you think, is it heavier than you? So I am 70 kilos, and is it typically air in the room? Is it is it going to be like total amount of air in this room? Is it 1 kilo, 10 kilos, 100 kilos, 1,000 kilos? How much do you think the air in the room weighs? We don't feel anything at all. We don't feel that the air has weight. I can easily move my arms through it. Doesn't seem like air is very heavy. So why don't you guess and put the answer on the chat, on the comments? What do you think? Who is heavier? The air in the room or you? So
air in the room is heavier.
Air in the room is heavier. Okay, air in the room is heavier.
This is by Swadhini Sahu.
Swadhini says air in the room is heavier. Okay, that seems not intuitive. So let's try and weigh the air in the room.
Why
Shall
not?
we try and weigh?
Yes.
Okay, let's try and weigh some air. And you can do this experiment in many ways. We can do it. We can calculate what is the weight of the air in the room. We can do that.
I'm also saying air must be way less heavy.
Air must be
Way less heavy.
Air must be way less heavy. Okay, so now remember what we asked for the total weight of the air in the room, and air must be way less heavy. So the best thing to do is let us
sample the thing.
Do it. So what we have is a balloon. So can you just show the balloon? Show the balloon. Camera. Yeah. So what we'll do is we'll try and fill the balloon up. Just blow the balloon and show a filled balloon without tying it. Just blow a balloon. And what we will do is we will take a balloon and we'll blow a balloon up and we'll see if we can weigh this balloon before and after. Okay. So let me just tilt the camera again. We can
now.
Yeah, I'm what we have, just to show you the setup here. I know you can't read the numbers, but don't worry so much. What you have to believe is this little thing is not a mobile phone, though it looks like one. It's basically a weighing machine. It's a small digital weighing machine. Oops, I seem to have locked it. And it has a screen. Because of the lights here, you can't really see the numbers on it, but it tells me the weight in something, 7.29 grams or something. It tells me the weight of whatever I keep on it. Okay. And what we've done is we've adjusted it. We've kept, again, we need a thing to keep our balloon on, and we are just using our little tube that we had. And we're going to keep the balloon on it and see what is the weight of the balloon. And you have to believe the numbers I tell you, because I know you can't read it from there. It weighs 1.16 grams. 1.16 grams. Okay, that's the weight of the balloon. And what we're going to do is we're just going to fill it up. We're going to blow it to the balloon and weigh it. And this is a typical kitchen weighing balance. If you have a weighing balance that's accurate to even 0.1 gram, you can try to weigh the air in the balloon.
Balancing the balloon is going to be
okay. Now it's going to be a little challenge to balance the balloon. The tear is off for some reason. I think the paper is touching the sides.
just a minute. Okay.
Yeah, it's fine. It's fine. Okay. So now we're going to try and keep the balloon on it, and again weigh it.
It's point.
No. It flew off.
It flew off. There's a lot of draft because of the air conditioning.
Yeah, the air conditioning here is going to make it difficult, but 1.35, something of that sort was the max, right? 3.5. Okay. Initially it was 1.1 something, right?
Yes. 1.16.
1.1 and 1.35. So 1.1. So let's say 1.535. About certainly 0.2 grams. Okay. So even this little balloon, this let's go back here. So what we did is we blew up a balloon and put it on the weighing machine, and even that little balloon. Okay, so even that little, the air in the balloon had a weight of 0.2 grams. I don't know how accurate the balance is. This is just a standard kitchen balance, not very accurate. So you can even weigh air. Okay, and let's just imagine, is this? It seems a little less actually. Should be a bit more, because I would think this is about a liter. This is about a liter, and air weighs approximately a gram a liter. That's a good number to know. And in fact, for those who are watching, who are not school students, but maybe if you're in high school or college, and you've heard the name of this famous gentleman in science called Mr. Avogadro, and Avogadro's number, if you've heard of this, and at some point in your life, if you went, if you in your 10th standard or something, they would have told you that there was something called a mole, right? And a mole of any gas at whatever condition, standard temperature, pressure, occupied a certain volume. And that volume, if you remember from way back in school or something, was 22.4 liters, right? 22.4 liters. And you know that what is air? Air is nitrogen and oxygen. Let's say mostly nitrogen. Nitrogen N2, 28 grams. So 28 grams occupies 22 liters. So that's approximately 1 gram a liter, slightly more, maybe 1.2 grams a liter. Okay. So if it's 1.2 grams a liter, then air is actually quite heavy. If you take a room, if you take a typical room, not this, it's the lecture theater in TIFR, but a typical room might be about 10 feet, 3 meters tall, maybe about 5 meters this way, and another, say, 5 meters that way. So if I have 5 into 5, 25, 25 into 3 is 75. Let's make it 5 into 4, or that will be 20. 20, right? 5 into 4 meters is small. 5 into 6, 30. 30 into 3 meters height is 90. I'll make it 100. See, I love doing approximations. In fact, I should just do a chime on how to just get approximate answers. Physicists, we love numbers like 1, 10, and 100. Right? You just calculate what's the nearest thing. So remember I said 28 grams and 22 means it's about 1. We divide, it's about 1. Okay. So what did we say? It's about 1 gram per liter. And I have something which is in meters now. We have in meters. So we have 5 and 4. 5 fours are 20. Right? No, 5 sixes. 5 and 6. 5 sixes are 30. 33s are 90. So I have 90 meter cube. Okay. 90 meter cube. Now remember, a meter cube is 1,000 liters. Right? So if 1 liter weighs 1 gram, approximately. Then 1,000 liters weighs 1 kilogram. So it's 1 kilogram per meter cube. And if you have something like a room which is 90 meter cube, the air weighs 90 kilograms, which is certainly heavier than you. So the next time somebody says that estimate the weight of the air in the room, it is much heavier than you. So don't think that the air doesn't have weight. But the weight of the air depends on a lot of things. The weight of the air obviously depends on how densely packed, how tightly packed the molecules are, how close they are to each other. Right? If the molecules come very close to each other, density will go up. If the molecules move away from each other, the density will go down. And another very easy experiment to do is to see, hot air balloons, they rise up. That's because they're less dense. So you can make some balloons at home simply with little paper bags. So yesterday I had gone to get some groceries, and I just don't think GeoMart is going to be very happy because I stole some bags. So I have some paper bags. Okay. And what we're going to do, we're going to balance some paper bags and try and see if we can see which one is lighter. All right. So here's a little setup which we have painstakingly made. I'm going to try and get all the rest of the extra out of here so we don't clutter the place up. And we can do it so that it is, we can move it down a bit. Okay, so what we have are two paper bags, and if you'd like to do this at home, this is going to take you some time because you need to get two paper bags which are almost the same size. Okay, and you have to balance them, and the way we balance them is we've just taken a stick, balance the stick first at the center so that the stick is absolutely horizontal, and then tied some string and taped it to the bags, and then balance them exactly so that the thing is horizontal. Okay, this thing is horizontal, and now the idea is we want to heat up the air. Unfortunately, we are not allowed to light a fire anymore. We can't light a candle. The easiest thing would be to light a candle below the bag. At home, I would do that. Just light a candle below the bag. So what we have is just a bulb. Just turn it off. It's like, yeah. So we just have a bulb, good old incandescent bulb. They still mostly they're being replaced by LED lamps, but you still get these bulbs. And as you know, a bulb generates a lot of heat. And hopefully, what we will do is we just use the bulb to heat up some air. Oops, I should not.
No, just don't leave it. It will settle. It will settle.
Let's keep this here. Let it settle. Let it settle down, and it's straight. No, it's not straight.
It's not straight.
I must have moved it. I have disturbed it. So let's first get it straight. And the other reason I've kept it here is it straight? The one way to look at it straight is look at that line and look at the edge of this. That's why we kept this here.
Look at this rod, and this is a 90-degree.
Yeah, or you can look at it's parallel to the edge of the this. And if this tilts, you clearly see this thing tilting. So it's a very sensitive way to check something. And let's start heating. So what we're trying to do is make it slightly warm. Give it some time. Can we see whether it is?
It's already started tilting.
Yeah. Can you see it has actually started tilting? Because if you look at the distance, let me see if I can mark it virtually on the screen. If you look at the distance on this side versus on that side, earlier they were absolutely parallel. This line and the base of the thing. Hopefully, once it gets hot, this is not in the center.
It's there. It's very clear.
Yeah. You can see it.
You can see it on screen. Okay. All right. Of course, we should not believe this. We should not believe this done only on one side. We should replicate the experiment on the other side. But let it just get hot for a minute, so you can clearly see the deflection. What we have is, I mean, it's not a hot air balloon that's just going to go and rise up and go away. But at least, and this is again, if you had a candle, it would be much easier to do this experiment with a candle, where you can really heat it up. But the only thing we could find was a light bulb. Light bulb also gets it hot, but not very hot, and also it's sort of,
So now you can see the tilt very prominently. To move out,
yeah, I can move out, so you can see the tilt. You can clearly see it's tilted It's no longer parallel to the edge of our board. Okay, and now let's switch this off, and hopefully once it cools down, it will start coming back. It's going to take some time, and in that time, I want you to definitely give me one answer, one very important answer. Please put this answer in the comments or the chat. The question that I'm going to ask you is, at what temperature does water boil? Very simple question. At what temperature does water boil? And if you're giving me a temperature, don't give me just a number. Please tell me a unit as well, because out here, especially in TIFR, there are a lot of people who don't, most of us think in terms of what's 30 degrees and all, but there are guys who think that it's 305 degrees Kelvin, or not degrees, but 305 Kelvin or something. So please at least put the units in. At what temperature does water boil? Okay. 373 Kelvin says someone. Let's see if they can, normally whatever units we use at home.
100 degrees Celsius.
Somebody says 100 degrees Celsius. You can also tell me if I'm not asking a good question. If my question is not well framed, you can tell me that also, that you're not asking a good question. You should ask, my question is wrong in some way, or my question doesn't make sense. You can also tell me that, not a problem. But the question is, at what temperature does water boil? Because we're going to come to that in just a little bit of time. Okay. And do we have a marker? We don't even have. We bring the marker. No, we don't have a marker. Okay, how's our board doing? It is still not balanced because it's still warm.
Someone asked at sea level.
At sea level. At sea level. Very good. Very good. Somebody's asking at sea level. That's absolutely correct. Water boils at some temperature at sea level. So you mean if I took it to Mount Everest, water would not boil at 100 degrees C or 373 K?
Someone said 212 degree Fahrenheit.
212 degree Fahrenheit. Ah, okay. This is a scale I haven't heard in a. Well, I mean, yeah, the fever thermometers often tell you in Fahrenheit, but.
There's another reply saying 100 degrees Celsius, the water will start evaporating.
100 degrees Celsius, water will start evaporating. Okay. Then let me ask you one more question. So, at what temperature does water evaporate? Okay. So, two questions. At what temperature does water boil? And just looking at the answers coming in, I have a second question. At what temperature does water evaporate? Okay. And this is almost, you know what? Let's try and see if we can just do the other, heat the other one and see that we can put it back or something. Whatever, because this is going to take a while to cool down. There's no fan here. So. Okay, so now we clearly have a situation where this guy was the hotter one. And let's see if we can heat up the other side and try and make it go back to its parallel state. It's almost parallel. Not yet.
You have an answer to your question.
I have answers to the question. Okay.
At the same temperature at 373 degrees. Sorry, at what temperature the water evaporates?
So it evaporates. Mahuli Datta says it evaporates at all temperatures.
Okay, and somebody says at all temperatures between its boiling point and freezing point. Okay, very good.
You can see it.
Actually, the thing is moving. It's
No, it moved. It heated up and escaped the bulb.
Yeah, it actually got hot and went off the bulb.
Yeah.
Can we bring this back? Or?
Yeah, we will. You can see the tilt is the other way now.
Yeah, now I think you can clearly see that the tilt, which was earlier, remember I told you to watch the edge in parallel to this. Right now the tilt is such that it's gone the other way because we're hitting the other back. Okay, so this is just a always when you're doing an experiment, always try to do something which is like a sanity check, that if my experiment is correct, I should also be able to do it in a slightly different way to confirm that I'm doing it correctly. Okay. I mean, we're just trying to see what is the simplest way we can check. I mean, and remember this idea of having a rod that is straight. and looking at two lines which are parallel, it's very easy for your eye to detect if it's not parallel or if it's tilting. So this is a very, very simple way to check. You can, I think should have moved, the thing has moved a bit, but otherwise you can definitely see that this end right now over here, this end is higher than this end. This end has gone down because this is the bag which is not being heated. This is the heavier one, and you can clearly see it now. Okay, all right. Time to get this off, I think. Yeah. Okay. So let's stop this. Let's stop this experiment. Any comments on our okay, let's get this guy out of the way. No, nothing. No comments there.
Comments here.
Yeah, what's the comments on YouTube saying?
So at any temperature below boiling point and freezing point, when increasing the energy,
Okay.
evaporated at all temperatures.
So first, let me talk about the evaporation. It's the simpler one. The answer is water evaporates at all temperatures. All temperatures. Okay. And in school, people somehow miss this point out. Water evaporates at all temperatures. In fact, somebody says above freezing and boiling, but no, even like, have you kept a block of, if you keep your ice cubes in your refrigerator, in the freezer, after a month, you'll see that the ice cube is smaller because the ice has evaporated. Okay, ice has evaporated. And if you keep water out, obviously it evaporates. No? Otherwise, your clothes wouldn't dry. The fact that clothes dry when you keep them outside is because water evaporates. Okay. And as you have all pointed out, many of you have pointed out, water boils at 100 degrees C, 373 K, only at sea level. And somebody pointed out sea level. And not on Mount Everest. You've also probably heard that the boiling point of water reduces with altitude or something. And what is happening? It's again due to the air pressure. So which means, what is boiling? What do you mean by boiling? So anytime you have a liquid, any liquid, right, it's evaporating, right? And because it's evaporating, the molecules of the liquid, they are escaping from the surface. So you have a surface of a liquid, below this is liquid, above this is air. Okay. So from the surface, at the surface, there are some molecules that are going from the liquid to the air. Some water molecules are coming from the air to the liquid. There's some transport. Now imagine you have this in a sealed container. So for example, a bottle of water, which is half water, half air, right? Now there will be we have a bottle which is, I can get a bottle which is half filled. Yeah. Drinking water. No drinking water. Okay, so here's a bottle which is half full of water. Slightly less than half now, but here's a bottle half full of water. And if I keep this bottle shut, after some time, the number of molecules that will come, initially right now there is probably very few molecules in this part here because it's mostly air from the room. Slowly the water is going to evaporate, and after some time, the number of water molecules inside this little volume will be constant. And for a given temperature, obviously if I heat the liquid, more water molecules will evaporate. So for a given temperature, there is a certain what is called a vapor pressure. If you keep a liquid, there's a vapor, the vapor has a pressure. Okay, that's vapor pressure. Just reducing the amount of water in your bottle.
No problem.
And if the vapor pressure is the same as the outside pressure, then that's what is boiling. That's when the liquid has no problem in going from the liquid state to the gas state. So now the experiment that we're going to do, actually it's got a very cool name. I don't have a pen or a marker with me. We don't have the marker here, right? Somehow the marker is gone, but it's okay. I have a pen. And I'm going to give you a hint of what the experiment is by just writing what this experiment is called. And this is called, it's called boiling. I will hold this up. questions, but let me just tell you the name of this experiment. I wanted to write it on the marker, but here it is. It is called boiling water. I hope you got the joke, for those who did. If not, don't worry, I'm going to explain it. This is boiling water. Okay, this is question.
Is ice turning into water called evaporation?
Is ice turning into water called evaporation? I would think so. I don't know what else to call it. Where we can turn it, you can call it ice turning into water vapor. You can call it sublimation. It's more technical, but I mean, I don't think evaporation would be wrong. But I'm not, you know, I'm not the dictionary person to know the English names for it. So now remember that when does a liquid boil? A liquid boils when the vapor pressure outside becomes equal to the atmospheric pressure. And the reason the temperature at which water boils reduces as you go up from, let's say, Mumbai to Simla or Darjeeling or wherever, is because of altitude, the atmospheric pressure is going down. So instead of boiling at maybe 100 degrees in Mumbai at sea level, it will boil at maybe 94 degrees or something as you go up, which is why it's, you know, it's difficult to cook stuff at high altitudes. So how do I show you this thing over here? I can make water boil right here, okay, at atmospheric pressure locally by changing the pressure. And it's very easy to change the pressure using a syringe. So we'll do this from scratch. We'll just get into the other syringe. So how do I locally reduce the pressure? So let me do this way. Are we going to do this in front of the syringe over here?
Yeah.
So I have a standard syringe, okay, and I will fill water in the syringe. And if I pull the piston out, okay, what happens is, of course, right now this was not capped, so there is the pressure inside. This is atmospheric pressure. But if I hold this shut, okay, and I pull this, it goes back. Why? Because I created a vacuum over here. The pressure was low. When I release it, it goes back. So now imagine if I had water here and I pulled the syringe. I can hold it pulled. Of course, I have to apply some force to hold it pulled. What would happen? The local pressure above the water would get reduced, which means its boiling point would get reduced. And hopefully, I can check if I can just make it boil at whatever is the room temperature over here. It's a little air-conditioned room here, so maybe it's a little difficult. So what we've done is, now, of course, as you can probably see from my finger, it's not very comfortable to hold this like this for a long time, because it hurts your finger when you pull it. So what we did is we got one of these. You can do this with your finger. By the way, you can do it. I'll show you. You can do it with your finger. But given that I've been practicing this a few times, we got one of these things which are used for when you have a intravenous thing, a thing which allows you to, you know, it's a little valve when they use for a vent flow or something. So I can just shut it. Okay, and this is slightly easier than you don't have to hold it. And what we've done here is, if you see this carefully, we filled about 2 milliliters of water in this. Okay, and also very careful. Can you just get a glass of water? We'll show them how to do it, because we'll show them the problem with the bubbles. If you're doing it at home, it's very important that you get rid of bubbles. Okay, because otherwise you won't know whether the water is boiling or it's just the air bubble that you had trapped. Okay, now if I suck some water in a syringe and I hold it, there will always be a tiny bubble at the top. Can you see this tiny bubble at the top? Okay. So whenever you pull the water in, you will take it from a glass and pull it in the syringe. Just make sure what you do is you just squirt the water out. That way you ensure there's no bubble. But again, you have to be very careful, because you hold it on top, squirt it out, and make sure every bubble is gone, and then catch it tightly. Because otherwise, even if you have the smallest bubble, you will get into a trouble. Okay, a bubble is trouble. Okay, and then you can shut it. You can shut it either with your finger, or in this case with this cap that we have. And simple, I am going to reduce the pressure by pulling it, and let's see what happens when we pull it. Okay, 1, 2, and 3. Can you see it starting to boil? Do it again. You will see bubbles coming out of the water. Okay, just watch this carefully. I'll hold it straight. Pull it down. Do you see the liquid starting to boil? Yes. Okay, let me try it with the finger. Just do it in front of them. Just start from scratch and do it in front of them. That way you start. You can do it with your finger. It hurts a bit. I've done it all morning. Okay, we get to. Yeah. Okay, let's try this one more time. Here you go. So that is it. Compressed. Hold your finger in it. 1 sec. It's not visible. Your hands are covering it. Your hands are covering it. Yeah, you can see it boiling. You'll have to do it one more time. Just look there and do it. It's easier. It stops boiling after some time, right? You should ask them why. Okay, redo from start again. Okay, so the question is, why is it boiling? Why is it boiling? And also, if you notice, the boiling stopped after a few seconds. It boils for a few seconds and it stops. So you need to also tell me why it stopped boiling. Okay, in the middle you said there was a question.
That was the question.
What?
Is ice turning into water?
I don't know.
Oh, ice turning. Okay, let's do this. Yeah, there. Yeah. Look at it. Follow it on the screen there. There's the water, little trapped water. Pulling it down. There it starts to boil.
It stopped boiling.
Yeah, it stopped boiling. Let me see with this one. Should I try this again? The other advantage of using this little thing to seal it is it helps in removing the bubble as well, because what I can do is I can open it and sort of chuck the water out of one end. And then lock it into position again. So now here I am with water in this tube, and pull the piston down. There it starts boiling, it's boiling, and the boiling will stop after a bit. Okay, one more time. Okay. 1, 2, and there you go. And there the water boils.
Yes, it can be seen.
Okay, it can be seen. All right. So now why did the water boil? And the water boiled, so you can get in the syringe, you can show that water boils even at room temperature if you reduce the pressure sufficiently above it. So whenever the vapor pressure becomes equal to the local pressure on top, the liquid starts boiling. Okay. So what we were doing in the syringe, by pulling the syringe down, we are reducing the pressure on top. Okay. When the pressure goes down, at some point, the pressure becomes equal to whatever is the vapor pressure of the water at our temperature around here, and the water starts boiling. Now, why did it stop boiling? That's the next question. So the reason it stopped boiling is also easy to sort of intuitively understand. Remember that when you want to make water boil at home, how do you make water boil at home? You don't reduce the pressure. You do something else to it. What do you do when you want to make water boil at home? You just keep it starts boiling? No, you have to add heat to it. You put it on the gas, or you put it on electric water boiler or something. You are adding energy to the water to make it boil. Agreed? Yes. And as long as I keep adding the energy, the water will boil. There is something called latent heat that the water needs. You need to supply it some heat to change from the liquid state to go into the gaseous phase. Now, in this case, I had reduced the pressure on top so that it became sort of less than the vapor pressure at the temperature. So the liquid starts boiling. But once the liquid starts boiling, that process takes heat. Where does the heat come from? There's no gas or electric over here, right? So the heat has to come from the water itself. So the water starts cooling down a bit. And once the water cools down, the vapor pressure is going to go down. So it means you require even lesser pressure to make it boil, and it will stop boiling at that particular pressure. So we can do this in 2 steps. Maybe I'll show it to you that it'll be easier to, okay, let's just try it if I can do it in 2 steps. That over here, let's see if I can, no, this has got a bubble in it. There. It's got a bubble. I'll have to throw the water out. Okay, we're going to try doing the bigger syringe.
Yeah.
Okay. Will it fit it?
Yeah.
All right. We'll just see if we can do a bigger syringe for better visibility. But I hope you got this argument that keep the water boiling. If I have to keep the water boiling, I need to supply energy to it.
Is it?
Okay. You can see the bubbles starting to come.
And there's a vapor inside the thing now.
And you can also see vapor inside. You can just see that there is, okay, it's probably a little difficult to see.
Could you see it?
So, yeah, it's difficult to do. It's much, the 50 ml syringe is probably easier to see. On the other hand, it's harder to do because you have to really hold it tight in order. Can I get my cap back?
Yeah.
Let's try this again. So I filled some water. I am going to put this, no, wrong one, doesn't matter. Okay, I will put my cap, I will turn it so that I can get the water out. Get the water out here, and then it is locked. So now I have this without a bubble, and 1, 2, 3, yank, water starts boiling and stops. Okay, now let me see if I can yank it again. Yank, and the water starts boiling again. Okay, so what happens is as it cools down, you have to reduce the pressure even more to make the water boil. Okay, that is the thing, but you can make water boil at room temperature. You have to reduce the pressure sufficiently. Now, if you're doing it at home, if you're doing it with your finger, you want to cheat a bit. What you can do is don't start with tap water, which is very cold. Start with water, which is say at, like
2 or 3 degrees.
Lukewarm. Start with water, which is at 30 degrees or 40 degrees or something. It'll be much, much easier because to really make the cold water from the tap boil, you have to suck it really hard. And for the 10 ml syringe, it happens just at the end of the syringe, which is sometimes a bit difficult. So you can just use, if you're doing the experiment at 12 o'clock right now, the water outside is quite hot anyway. You're blocking the view. So it's a little difficult with you can use the stopper. Yes. Okay, so that was our experiment on boiling water, BOILE. And if you got the joke, it's because of Boyle's law. This is exactly what Boyle's law is. That's that pressure 1, volume 1, pressure 2, volume 2. So this is the same Boyle. And what we did is we reduced the pressure by putting it down. By increasing the volume, we reduced the pressure, which is why it was boiling. Okay, so yeah, it's already past time. So I think we will allow you to ask your questions. So please ask whatever questions you wanted on these experiments. And meanwhile, okay, so Remy is going to try one more time. I think it's fascinating to make water boil at room temperature. And you can actually see the vapor in this. In this one, it's nice. In the big tube, you can see the vapor, which it's a little difficult in the small tube. But you require a lot of strength to actually be able to do this experiment. It's tough to maintain a vacuum. You could do it with a vacuum pump and all, but then that's a little bit more challenging. It's not a home experiment anymore. Okay, so are there questions coming in? So if there are questions, please post your questions on the chats on YouTube and Facebook, and I will try and answer them. Okay, is there a question?
Regarding the air trapped inside the bubbles, does it solely come from the conversion of water? Regarding the air trapped inside the bubbles, does it solely come from the conversion of water?
Oh, that is actually a very, very, very good question. Does the bubbles, are they coming from the conversion, the boiling of water, or is it dissolved air that is coming out? And yes, I should have mentioned this. Actually, it's always better to start with sort of boiled water, and which we did. In fact, we had initially nothing to hide. We had initially boiled the water here and then let it cool down, because you don't want there to be too many dissolved bubbles in the water. There's also dissolved air. So if you do it with just normal water, the first time you do it, you will remove the dissolved air from it. Right? The second time, third time you do it, once the air is all gone, you'll know that you have you'll know, because there'll be a residual bubble at the top. Whatever air is expelled will be a residual bubble at the top. Once that bubble is gone, you can remove the bubble, just throw out the water and then suck it again. You'll make the water boil. But yes, you have to make sure that there's no dissolved air in the water. The easiest thing to do is just heat up the water first and just remove all the bubbles. Okay, other questions?
Yeah. How does water give heat itself?
How does water give heat itself? Well, it's just like, when you keep your chai outside. This is chai and wire. The chai cools down, right? The chai cools down because the evaporation, the more energetic molecules evaporate, right? What is left behind is lower energy, so it's lower in temperature. And similarly, if something has to boil, it needs energy. It's going to take that energy from the sort of internal energy of the water molecules that are there. So the water molecules, their energy will go down because of the fact that you've converted some to vapor and it's gone outside. So that's how the heat is coming sort of from the water itself. The water is going to cool down slightly, not much, little.
You have one more question.
Yes, go ahead.
In the inverted bottle experiment, off the top bottle has helium instead of air. will the water fall down quicker or is gravity the factor?
Okay, that's a nice question. Whoever is asking that, thank you. It's a very interesting question. Let me repeat it. In our tornado experiment, when we had two bottles, now of course right now we have air in this bottle. What would happen if there was helium in this bottle? Would it be faster? Okay. Also, what is important is the the density factor, that this is air right now, and if I turn it this way and I have helium. Now, obviously, if I had helium, the helium would want to go up because it's less dense. It would want to go up slightly faster. But remember, the density difference between water and air. Air is, what did I say, 1 gram, approximately 1 gram per centimeter cube, right? Sorry, 1 gram per liter. Water is 1 kilogram per liter. So there's a factor 1000 in density right now. Instead of the factor 1000, if I change this from air to helium, yes, it will be slightly changed, but it won't be a huge factor. It's not that we're going to go from 1000 to a million. We might go from 1000. What's the density of helium? I don't know, but let's say the density of helium is half that of air. It's a factor of 2. It's not a factor of 10. So out here, the density difference between water and air, or water and the gas, is much larger than the two gases. So you will see a slight difference, but not very much. But very good question. Very good question. Okay. Other questions? Are there questions coming on Facebook? Divya Shankar, are there questions on Facebook? If there are, please unmute yourself and tell me the question, because I'm not monitoring it right now. Yeah, any more questions on YouTube?
No.
No. Oh, are you monitoring Facebook as well?
No,
you're not. Okay. So, yeah, any question on Facebook? We still have about 3 or 4 minutes that we can do this.
There are a few questions on Facebook.
Yeah, go ahead. Tell me the question on Facebook.
If water boils, does it translate into vapor?
If water boils?
Does it translate into vapor?
If water boils, does it translate into vapor? Yes. I mean, water is going from water liquid to water gas, which you call water vapor. Right? So, yes. I mean, boiling happens, evaporation happens at the surface. Boiling happens at all points inside the liquid. As you saw, all points inside the liquid were boiling. Okay, that's the main difference. Okay, any other questions? Facebook? Thank you. So remember that certainly water boils. If somebody asks you at what temperature does water boils, you can tell them, well, tell me what the ambient pressure is. Right? If the ambient pressure is low, water will boil at a much lower temperature. That's what we just showed you. And also, at what temperature does water evaporate? Water evaporates at all temperatures, effectively. Okay. And if there are no more questions,
there is one question on Facebook.
Yeah.
The air we blow out would still be mostly nitrogen, but would be carbon dioxide. The air we blow out would still be mostly nitrogen, but would be carbon dioxide, replace oxygen as we breathe out. And
okay, very good question. So when we were measuring the density of air using the balloon, right? Okay, I did an experiment assuming air is actually assumed 100% nitrogen, but yes, I mean, there will be some carbon dioxide in this, which will change the density slightly. So the density of exhaled breath will be more. But please remember that we use only, we breathe in air, which is about, say, whatever, 78 or 80% nitrogen, 20% oxygen. But that 20% oxygen, we don't use all of it. We hardly use about 4% is what we use to convert it to carbon dioxide. 16% or so is still oxygen. Okay. So this thing will have 80% nitrogen is not changed, but instead of 20% oxygen, you have 16% oxygen and only 4% carbon dioxide. So yes, that 4% carbon dioxide is certainly heavier than the 4% oxygen it has replaced. But again, overall, it's not going to be a very big change because you still have only 4% which is carbon dioxide. Yes.
You have two more questions on.
Keep going.
Why did tilting the bottle make it come out more quickly?
Very good question. Tilting the bottle, if you noticed, make it come out quickly. And if I can just show you over here, Now, if initially when the bottle is full, obviously there's not much, but once the bottle has even a little bit of the air out, once you tilt it, you're allowing water to go from down, but you're leaving space on top for the air to come inside. So the air can fill the bottle, get inside the bottle from top of the water. It can slide on top of the water and get in, unless you tilt it like this, where there's no space for the air. But normally you tilt it like this, giving enough space for air to come out, and then obviously the water can drain out quicker because the air can go in. That's why we tilt it.
What are the applications of the syringe experiment?
The applications of the syringe experiment. Well, I don't know. It's just to show you that water could boil under reduced pressures, but the fact that liquids boil under reduced pressure is often used when you want to purify liquids. Right? You may not want to be people often do distillations, etc., under reduced pressure, which makes it easier for you to sort of you don't have to heat it up to that much of a temperature. So people use it in, for example, purification experiments. So that's what I can think of immediately. But yeah, the idea that you can change pressures and control boiling points or something is obviously, you use the inverse of it. I increase the pressure to get the boiling point up when I use a pressure cooker. The reason a pressure cooker cooks quicker is because if I put a little weight on it, now the pressure inside has to exceed atmospheric pressure plus that weight. So there's more pressure. So if you're at Mumbai, for example, the water boiling inside would probably boil around maybe 120 degrees or so, or it's like maybe 100 something more. An autoclave would be 120 degrees typically with some pressure. And then if you were in the Himalayas somewhere, even though the atmospheric pressure has gone down, I have added some weight, so the water will still boil, let's say 100 or 105 or something, much better than what it would do without the weight. So we do use increase in pressure to elevate the boiling point as well. So we do both. We reduce the pressure for distillations and we increase the pressure in pressure cooker. So here there are two examples right there. Okay. Anything else? Okay. If not, it's past 12:15. Thank you very much for joining us on this online Chai and Why. We will be back in 2 weeks. Mid-September is our typical session where we look at one of two things. September 15th, the middle of the month, is in India, it's Engineers Day, and it's also International Design Day, right? So there's the International Dot Day. You can Google that. And we usually will have something to do with one of these themes coming up. The next time we will put it out on the Facebook and Twitter channels that we have and send you an email if you're part of our mailing list. If you'd like to join our mailing list, please send an email to outreach, outreach @tifr.res.in, or follow us on Facebook or Twitter. That's also possible. You will be updated with what's going on. Meanwhile, do remember, unlock does not mean unmask. So if you're going outside, if you're in a place where there are people, you cannot maintain enough distance, be sure to wear a mask and stay safe, and goodbye for now. Thank you.